don't forget, every one of these lectures is recorded. I've been trying to send out a note, an announcement in Canvas to make sure you guys see that they're recorded. But if I forget to send out the announcement, I do record the lectures, and you can go into OneNote, and on the page that they're recorded on, here, let me show you. For example, if I went to Systems of Linear Equations, which would have been last Wednesday, you can see at the top of the page, there's that blue link. That link will take you to the recording of that lecture. So today's lecture, of course, will be recorded as well, and there will be a link to it, and I'll try and send out an announcement. Hopefully I won't forget. So we're going to do some polynomial long division, but first I want to just remember what we did a week ago on Monday. And we talked about polynomial graphs. And my idea in my head, whether I communicated this well or not, was that you would, the motivating idea is that what can we tell about the graph of a polynomial just by looking at it, just by looking at the properties of the polynomial? So can we tell anything about the shape of the graph of the polynomial just by, for example, looking at the degree of the polynomial, or by looking at the leading coefficient, or by looking at the number of terms? And it turns out that most of what you can tell about the possibilities for a graph of a polynomial come from looking at the leading coefficient. So the leading term and the leading coefficient. The flip side of that is, and we discussed this a little bit as well, is looking at the graph, is there anything I can say about the polynomial? And I did a little bit less of that, but I just want to gather all this information up into one place. So for polynomial graphs, the overall shape of the graph of a polynomial will be determined, or the same as, I guess determined is a better word. That's what I had written here in my notes. By the leading term. For example, let's do a few examples. Suppose I gave you this function, let's say minus 3x to the fifth plus 4x cubed plus 7x squared plus 5x plus 1. So that is a long old polynomial. The case I was trying to make last time is that if I want to determine the overall behavior of this thing, I really only have to look at the first term. So we did that a little review today. And the first term says it's a negative leading coefficient. So it's a negative leading coefficient. That's the negative 3. That's the negative leading coefficient. And an odd degree. So that's the 5. The power of 5 is an odd number. So it's an odd power. That's all the odd means. It's odd or even. And then the leading coefficient, it can be positive or negative. So for this one, the overall shape of this graph for large values of x is, well, it's odd and it's negative, so it's going to go up to the left and down to the right. How would I know that? Well, I gave you a list of all the possibilities in the last lecture. And there's only 4, right? So I could do another example if I had f of x is equal to 7x to the 6th plus 5x squared plus 7. I want to make it short because I'm tired of writing. But I could have a bunch of terms in there. I only have to look at the first term to tell its sort of end behavior, its overall shape for large values. And again, what is this? I've got a positive leading coefficient and a degree is even. I don't even have to think about what power of even, right? I just have to think about even and odd. So I know for the end behavior, there might be crazy stuff close in, but for the end behavior, it's going to go up in both directions. So it's a positive even polynomial. What else could we tell from the degree of a polynomial? A polynomial can have at most the same number of roots as its degree. Now, that's an awkward sentence, and I always try and write things differently from the book so you guys get a little contrast, but it's an awkward sentence. Hopefully that makes sense. So, for example, a 6th degree polynomial can have at most 6 roots. In other words, it can cross the axis at most 6 times. A 5th degree polynomial can have at most 5 roots. So we could say example, this polynomial has degree 5. This can have at most 5 roots, or can cross the x-axis at most 5 times. Now it can cross fewer than 5 times, but it can't cross more. And the reason that doesn't give us a great rule, right? It puts an upper bound on things, but it doesn't tell us that we can say exactly how many roots there are just by looking at the leading term. It requires more analysis. In fact, some of that analysis we're going to do today. What else did we have? A polynomial can have at most one less turning point. Then its degree. So what's a turning point? A turning point is like that. So for example, this graph has 2 turning points. In other words, it starts coming down. Let's see, if I were traveling along this graph, I'd travel, and then suddenly I'd be going from down to up, and I'd be going up, and then I'd be going down again. So it's 2 turning points. It goes from going down to going up, and going up to going down. So this has 2 turning points. So the least degree it could have is, well, 2 plus 1, which is 3. So this could be a cubic polynomial. In fact, it looks like a cubic polynomial. But that's a little deceiving. I do know it's an odd polynomial because it goes up one direction and down the other, right? So even polynomials always go either both up or both down. But you can't necessarily tell from the number of turning points exactly what polynomial it is. Usually you can only tell, sort of put a minimum bound on it. So I know this turns twice, so it can't be a degree 1 or degree 2 polynomial. It's got to be degree 3 or more. Could be a 5th degree polynomial though, right? So we defined maximums and minimums. And there's another way of thinking about the number of turning points. Or let me put it this way. I don't like the way it's worded in my notes. The total number of maximums and minimums, so local maximums and local minimums, right? The tops and bottoms of the tops of hills and bottoms of valleys. The total number of maximums and minimums is equal to the number of turning points. So when you go from going up to going down, you get a maximum. When you go from going down to going up, you get a minimum. And since it can have a limited number of turning points for a given polynomial, you can just count those, and that also gives you some sense of the possible degree of the polynomial. So we'd like to explore polynomials in a little bit more detail. In particular, here's the way I want to think about polynomials. So suppose I can know the roots of a polynomial. Can I draw the graph? Yeah, so let's think about this for example. So suppose I gave you f of x is equal to, I don't know, let's go x minus 5, x minus 3, x plus 2, x plus 4. Suppose I gave you this polynomial. Now it's all in factored form, right? But if I multiplied this out, it would give me a big polynomial. What do I know about this polynomial? Well, I know this has roots of, well, everything that would make one of these terms 0 is going to give me a root. So it's going to have roots of x equals 5, x equals 3, x equals 0, x equals minus 2, and x equals minus 4. Now suppose I wanted to graph this. Well, what do I know? I know from this thing that it crosses the axis at, let's see, I'll draw this in a different color. Let's do green. At minus 4, minus 2, 0, 3, and 5. And what else do I know? Let's see, if I multiplied this all out, since there's x's in 1, 2, 3, 4, 5 terms, it would be a degree 5 polynomial. Everything in front of the x's is positive, so this would be a 5th degree polynomial with positive leading coefficient. Oops, I don't want to use my rainbow pen, unless you guys want me to use my rainbow pen. Please chime in if you like the rainbow pen more than I do. So it'll go up here and down here, right? Because it'll be a positive leading coefficient on a 5th degree polynomial. And then it's going to cross the axis everywhere. I've got a little hash mark in green, so it's going to cross there. It's going to cross there. Going to cross there. Going to cross there. And it's going to cross. I kind of missed my mark, but you get the idea. It's going to cross there. Notice, if I know the roots of the polynomial and the degree, I can sketch a graph faster than I can type it into Desmos. I'm a lousy typist, but maybe it's faster than you can as well. So our goal is to kind of think about, can we take a given polynomial and write it in factored form or in terms of its roots? And then can we draw the graph? When I took this class, well, it was a long time ago now. When I took this class in 1974 or 75, well, I can't remember when I took it. We didn't have any access to any graphing software at all. And usually we didn't even have books that had lots of graphs in them. So we had to use these processes that I'm gonna show you today to try and factor things. And we went into it in much greater detail because otherwise we couldn't have a picture of the functions at all. We'll do it in this class sort of polynomial evaluation light. So we won't go into as much detail as I had to when I did it, because you guys have this wonderful technology that you can go back and forth between what you know algebraically, what you've written down in pen and paper, and what you can do on your calculator or in Desmos or in GeoGebra, whichever program you like. Even OneNote will draw graphs for you, which is kind of amazing. So how can we get at those roots? Well, there's a little bit of mechanical stuff we have to go through to try and get at these roots. And it's something you may or may not have seen before. I'm not sure. I don't think you see it in the first half of this course. High schools sometimes teach it, sometimes don't. But it's polynomial long division. So this is going to be a tool we'll be able to use for finding roots. And here's sort of the idea. When you do regular division, what can you find out? So you can go like 375 divided by 15, if you remember how to do long division. And you go and you say, what can I multiply 15 by to get 30? And you say 2, so that's 30. You subtract, you get 7, you bring down the 5. And you say, oh, I can multiply 15 by something to get 75 maybe, or something close. So I go 15 times 15 plus 15 is 30, plus 15 is 45, plus 15 is 60, plus 15 is 75. Yeah, so it's 5. And if I multiply it out and I go 75 and I get 0. If I end up with a 0 here, I know that 15 divides 375. Or a better way to think of it is I can write 375 as 15 times 25. Now suppose it doesn't come out 0. Suppose I said 12 into 375. What information does it give me then? Well, it doesn't give quite the same information. It doesn't show that I can break 375 up into a product of two pieces, but it's close. So let's see. Let's see if I multiply that by 3, I get 36. I get 1, 5. So 3, 1, 12, and I get 3 there. This thing, if you remember, is called the remainder. And this thing is the I always forget the name of this, and I'm just forgetting my life here. Let's see. So what can I say? I can say 375. I'm sorry, I'm drawing a complete blank on the name. I'll remember it here. Maybe one of you guys knows. It's not in my notes, and I don't have the book necessarily open. So 375 is equal to, well, we can almost do the same thing. It's 12 times 31. But that doesn't quite get you to 375. You need 3 more. So the remainder, it's like the dividend and the quotient. Golly, I'm forgetting everything. And I didn't write it in my notes because I was sure I wouldn't forget. I'll have to clear that up on Wednesday because I want to keep going. The ideas are the same. The language, though, I'll have to clarify. So I can almost write 375 as a product, but I can write it as a product, and then I have to add the remainder in, yeah? So how does that apply to polynomial long division? In fact, what could polynomial long division possibly mean? Well, suppose I was given a rational function like this. I want to use the example that they use in the book here. 3x squared plus 9x plus 25. So suppose I'm given this rational function. I guess I'll call it f of x. It's 3x squared plus 9x plus 25. Darn it. I don't know why I wrote that so weirdly. 3x squared plus 9x plus 25. You guys are going to get tired of hearing that. And suppose I want to know, is 3 a root of this? In other words, is x minus 3 a factor of f of x? Well, remember what a factor is. A factor is like up here, to factor a polynomial is to write it in terms of a product. To factor a number is to write it in terms of a product. How do we tell if a number is evenly is a factor of one number is a factor of another number? Is we do long division, we do division. It turns out we can do the same thing. We can try division. So in other words, we're going to try dividing polynomials. So we're going to say, we're going to divide 3x squared plus 9x plus 25 by x minus 3. And if it goes in evenly, then we know it's a factor. So in other words, we can write 3x squared plus 9x plus 25 as a product of two polynomials, each of which will be a factor. So let's see how to do this. So the process is almost the same as what you're used to. You look at the first term, and you look at the first term here. You look at the first term under the radical, or under the I'm losing my words today. You look at the first term of the polynomial that's being divided and the first term of the polynomial you're dividing it by. Then you say, what can I multiply this thing here by to get that? And a little bit of thought will tell you, well, if I multiply x by 3x, then I'll get 3x squared. So I'm going to multiply this whole polynomial, or this whole factor, x minus 3, by 3x. And if I do that, I get 3x times x, that gives me 3x squared. And I have 3x times minus 3, which is minus 9x. I should write that in black pen, or maybe all in the same color. Sorry, there's a color scheme problem here, but hopefully that's not confusing. And now I want to subtract this thing from my polynomial. So I have 3x squared minus 3x squared, so I get 0. You should always get 0 for your first thing. Let's see, I have a 9x minus a minus 9x, so that's 18x. So I get... And then I bring down my next term. And I say now, what can I multiply x by to get 18x? Well, hopefully you can see that I multiply it by 18. So 18 times x is 18x. Boy, the colors are weird. And then minus, let's see, 3 times 18 is... let's see, 54, 54, I think. Don't be mean if I'm wrong about that being 54, by the way. I'm trying. And then I subtract these polynomials. And I'll get a 0. You should always get a 0 for the thing on the left. And let's see, I'll have 25 minus a minus 54. What that's... 79. I think I did that wrong, but that's all right. I mean, I think I added wrong somewhere. I don't think I did anything wrong. I think I added wrong though. But it doesn't matter. Plus 79, right? Because I have 25 minus a minus 54, so 79. So what does this tell me? Well, it's similar to what happened up here. First of all, it tells me that I didn't get 0 as my remainder. So remainder is not 0. So x minus 3 is not a factor of 3x squared plus 9x plus 25. What can I say? I can say, similar to what we said above, I can say x minus 3 times 3x plus 18 plus my remainder is my original polynomial. 3x squared plus 9x plus 25. And I do think I added wrong somewhere. But I can't see it. Maybe I didn't. That'd be amazing if I didn't actually add. So if the remainder were 0, notice that it would just be written as a product. But we didn't happen to have a remainder 0. So let's do another one. Let's do another example. let's just ask, is x plus 2 a factor of 5x cubed minus 6x squared minus 28x plus 8. It's not obvious by just looking at it. So let's check it out by doing long division. So we're going to do x plus 2, and we're going to see if it goes evenly into 5x cubed minus 6x squared plus 28x plus 8. Oops, I think that's a minus 28x. And go through the process and see if it can be written evenly. So first thing I do, let's see, what can I multiply x by to get 5x cubed? Well, clearly I can multiply by 5x squared. And if I do that, well, 5x squared times x is just 5x cubed. That should always work out, right? These two things have to always be the same. Then I multiply 5x squared by 2, and I get plus 10x squared. And I subtract these two things. And if I do that, I get minus, I get a 0. And I get a minus, let's see, a 6x squared minus 10x squared, so that's minus 16x squared. Then I bring down that next term. I think I'll do this all in black and green. So minus 28x. Now I need to know what I can multiply x by to get minus 16x squared. So if I multiply by minus 16x, I'll get the right thing. I'll get minus 16x squared. And then I multiply minus 16x times 2, so that's minus 32x. So let's see. This thing I'm going to subtract from the above polynomial. So I get minus 16x squared minus a negative 16x squared. That gives me minus 16x squared plus 16x squared, so I get a 0, and you should always get a 0 there. Then let's see, then I have minus 28x minus a minus 32x. Let's see, that ends up to be plus 4x. Then I'm going to bring down my next term, plus 8. The question is, what can I multiply x by to get 4x? Well, that's an easy one, right? I can just multiply x by 4, and I'll get 4x. Then I multiply 2 by 4, and I get 8. You can see what's going to happen here. I subtract these, and I get a 0 here. But now I also get a 0 in the last term, and there's nothing over here to bring down. So I'm done. So this has a remainder of 0. Fabulous. What have we shown? We've shown that now we can know, since it divides evenly, we know 5x cubed minus 6x squared minus 28x plus 8, which is a pretty ugly polynomial, is equal to x plus 2 times 5x squared minus 16x plus 4. We've teased out one of the factors, and there's no remainder, so it's plus 0. It doesn't matter. So that means x plus 2 is a root of this polynomial. So I know at least one of the roots. Now, this is just a quadratic, so I actually could find all 3 roots of this cubic. So this is a lesson in how polynomials are dealt with. So you couldn't possibly know this, but for applied mathematics, just sort of writ large in the world. So if you're doing heavy-duty applied mathematics in physics or chemistry or computer science or geoscience, or you're doing business models, lots of these models are polynomials. Polynomials can be very difficult to deal with, but one of the ways you can successfully deal with polynomials, if you want to factor them, which is often what you want to do, is if you can find one of the roots. Notice you can reduce it to, you can reduce the problem of factoring a cubic to, well, if I can find one of the roots, now I only have to factor a quadratic. You can imagine if you had a 5th degree polynomial and you could identify one of the roots, then it would bring it down to a 4th degree polynomial. And if you could identify one of those roots, you can kind of chip away at it by getting a root at a time and doing long division, reducing the problem to lower and lower degree. And once you get to a quadratic, well, we can always factor those. We have the quadratic equation. So I want to state some theorems that we kind of used, but I didn't state. There's 2 theorems. They're called the factor theorem and the remainder theorem. And probably if you asked a mathematician who was an applied mathematician, maybe not me, I'm not really an applied mathematician, they would say that these are the 2 biggest ideas, 2 of the biggest ideas you learned in this course. Now, it's kind of tucked into a million other ideas, right? This course is chock full of ideas. And these don't sound very important, but the factor theorem and the remainder theorem turn out to be big deals. So let me state them. The remainder theorem, because this is kind of surprising. If a polynomial is divided by x minus k, so x minus some number, right? Like up here in this problem we just did, k would be 2. So x minus k. The remainder is f of k. That's kind of surprising. Let me go up and see what that means. That means that when we got a remainder on this first one, if I'd have just put 3 into this polynomial here, if I'd have just put 3 into that polynomial, that would have been f of 3, right? I would get 79. So polynomial long division is sort of an odd way to evaluate a polynomial at a point. So long division. I can't think of whether that's used, strictly speaking, in that way ever, but I like that. I don't know how fast computers do polynomial long division, by the way. Probably slower than they calculate the value of polynomial. So that's the remainder theorem, which I kind of implied a little bit because the remainder is 0. Well, I won't go into that. So, and then the factor theorem. There are a couple things I'm going to want to clear up next class. So the factor theorem says, let me write it the same way the book does. Well, I don't do it exactly the same, but a polynomial I don't know if I do it the same. I don't have everything in front of me. A polynomial, f of x, has a factor, x minus k, if and only if f of k is equal to 0. Another way of, this is equivalent to, the two arrows, back-to-back arrows means equivalent to, if a polynomial is divided by x minus k, and has remainder, oops, I don't know why that popped open, 0, then f of k is equal to 0, and x minus k is a factor of f of x. So here's the honest truth. It's rarely necessary to actually do the long division of polynomials. Now, I would like you guys to practice it. You'll practice it Wednesday in lab. You'll practice it on your homework in my lab. It'll actually come up on the final, and not because I'm mean, but because we have a standard kind of set of questions for the final. And it will come up in upper division applied math problems in different contexts. So in particular in calculus, it'll come up again in calculus. But you don't usually have to do the long division. So let me give you an example. So consider f of x equal to 2x cubed plus 5x squared, I'm stuck on cubics today, minus x minus 6. So consider that polynomial. R, x plus 2, x plus 2/3, x minus 1 roots, or factors rather, of f of x. In other words, are any of these factors of f of x? Maybe all of them are. How could we do it? Well, there's a couple ways we could do it. Well, we could do the long division, and maybe we should do one for practice. So x plus 2 into 2x cubed plus 5x minus x minus 6. I'm going to do this fast and see if you guys can keep up. 2x squared, so I get 2x cubed plus 4, oops, that should be squared there. 4x squared, I subtract, I get a 0, I get x squared, I think positive x squared, I bring down the minus x, and I say minus x, and I get minus x squared minus 2x, I subtract, wait, I didn't want minus x squared, right? I wanted plus x squared, sorry. That's the problem with doing anything fast. I subtract, so I get a minus 2x. I get my 0 there as required. I bring down my 6. And I go minus 2, minus 2x, minus 4. Obviously those are different, so we're not going to get a remainder. We're going to get a remainder of minus 2. Because we subtract that now. I think I did something wrong there. I think I wanted it to work out. Ah! I did. Pretend class never started. We never arrived. So that never happened. Let's see. When I multiply x times 2, I get 2x. That's minus 3x there, I think. Minus 6. And now I multiply by minus 3. I get minus 3x minus 6. I get 0. So remainder 0. So it is a root, or so x plus 2 is a factor, and x equals minus 2 is a root. In other words, if I put minus 2 into this function, it'll give me a 0. It comes out 0. So it crosses the axis at minus 2. So it is a factor. But notice I could have checked to see if it was a factor just by calculating f of minus 2. And if I do that, it would be 2 times minus 2 cubed plus 5 times minus 2 squared minus some minus 2 minus 6, and this comes out to be minus 16 plus 20 plus 2 minus 6, which is plus 22 minus 22, 0. So this would have said f of minus 2 is 0, so that means x plus 2 is a factor. Right? You get that you can sort of conflate the remainder with the function value. Now, the problem with this is it doesn't tell me how it's factored. It tells me that 2 is a root. It tells me that x plus 2 is a factor. But to actually find this factor up here, I need to do long division. So what does that factor tell me? Remember what that's supposed to mean. That means if I take the x plus 2 and I multiply it by that, I should get my original function. So in other words, 5x cubed plus 5x squared, or 2x cubed rather, plus 5x squared minus x minus 6 can be written as a product of x plus 2 times 2x squared plus x minus 3. If I multiplied out that right-hand side, I would get that. So evaluating the function at a possible root will tell you if it's a root or not. And that tells you whether you figured out the factor or not. But it doesn't tell you how to break the polynomial up into pieces. So a lot of this is sort of talking in the air until you get to practice this. So I don't want to go too deep down this rabbit hole. I want to say one reason we use this is simplifying rational functions. So let's consider a rational function. Let's call it big R of x, because it's a big rational function. And this is 6x squared plus 5x plus 10 over 2x plus 3. Well, I always think of the fraction bar, or the bar in a rational function as division, right? Well, let's actually do polynomial division and see what we can get here. See if we can rewrite this. So if I do polynomial division sort of off to the side, like scratch work, I have 6x squared plus 5x plus 10. I'm going to divide that by 2x plus 3. And let's see, I'll do this fast. 3x, I get 6x squared. And 3x times 3 is 9x. I'm going to subtract this. So I get my 0 as expected, as hoped. And 5x minus 9x, well, that's a minus 4x. Let's see, and I bring down the 10, plus 10. Darn it. I have a little trouble writing, reading, speaking, adding, subtracting, dividing, and graphing. But other than that, I'm right on top of it. Oh, and remembering words. So if I multiply, what do I have to multiply 2x by to get minus 4x? I'm going to say minus 2. So I get minus 4x. That's good. That'll give me the 0 I need. And then minus 2 times 3 is minus 6. I'm going to subtract those. So I get my 0 there. Minus 4x. Minus 4x. So that's minus 4x plus 4x. That gives me 0. I have 10x minus, right, we're subtracting this, minus a minus 6x, so that's 10x plus 6x, so that's 16. So I have a remainder of 16. So in other words, 2x plus 3, so if you remember how fractions can be rewritten, this will end up being, and maybe I'll do an example of that, this will end up being 3x minus 2 plus 16 over 2x plus 3. So if I had to put this over a common denominator, I'd multiply by 2x plus 3 or 2x plus 3, and I'd get the right polynomial on top. So that's supposed to be similar to, suppose I were given something like 81/5, and we wanted to simplify this. We would get the number of times 5 goes into it, a whole number of times 5 goes into it, and then the remainder. So 5 goes into 81. How many times? Well, 1, 5, 8 minus 5 is 3, 1. So we get 16. And I have 1 left over, so that's my remainder. So in other words, 81 over 5 is the same as 16 and 1/5. In the same, this is the whole number of divisions. This is how many whole sort of polynomial times 2x plus 3 goes into 6x squared plus 5x plus 10. And then there's a fractional part left over, 16 over 2x plus 3. So I'm not going to apply that right now. I've been talking pretty much straight through. and pretty fast, I think. So don't forget there's a video for this, and it might bear watching this video again if some of this went by kind of fast. I don't want to keep you guys late, so I'm gonna kind of put off the last idea I want to discuss, which would probably take 12 to 15 minutes. So I'm going to stop the lecture now. Don't forget to upload your labs, and if you're still having trouble uploading your labs, make sure to contact me. If all else fails, just email them to me. You do have my lab assignment. Don't forget to check in on my lab. You guys have been, for the most part, pretty darn good at checking in and doing your my lab stuff, and I haven't really been harping on it. So most of you don't need it, so don't feel like I'm picking on you. But a few of you haven't been on there or are a little bit behind, and a couple of people had trouble getting their registration and stuff. So if you're a little bit behind, let me know, and we'll make sure we get you caught up. We're all going to go through this course as much as we can at the same pace. But if you fall behind a little bit, I'm gonna try not to just pitch you to the wolves. I'm gonna try and keep you up with us. But I won't know. I have hundreds of students, so I won't necessarily notice. So please don't suffer in silence if you're worried. That said, I'm gonna stop my recording.